Okay, so now we're going to look at is this idea of shifting our perspective from a linear system to an angular system. And so when an object is moving around in a circle consistently, like rotating in a circle, it's changing both its x and its y position. So it's easier to look at the motion in terms of angular quantities, okay? If you kind of thought about it, if I had an object that was moving kind of around, and I were to just kind of project it on the classic Cartesian coordinate system, if I were to start at this position here and go here, I would have like an x value and a y value, x1, y1, and then here would be an x2 and a y2. If instead I looked at it in terms of an angular viewpoint, if I were to go from here to here, my radius isn't changing in this case, but my angle is changing. I'm going from this theta value to this theta value. So angular movement or circular movement is kind of easier to look at from a theta perspective than it is from an x and a y perspective. So some things to kind of keep in mind, since we're going to shift our perspective a little bit, is that as you go around in a circle, you can think of that angle value as being measured in terms of degrees or in terms of radians, okay? So going around once, one revolution is 360 degrees, or you can think of one revolution as equal to 2 pi radians, okay? So just a different unit of measurement. It's a little bit easier to use the units of radians because it's easier to count. So going around once is 2 pi, going around twice is 4 pi, going around 3 times is 6 pi, 4 times is 8 pi. Whereas if you were to think about this in terms of degree, going around once is 360 degrees, going around twice is 720 degrees, around 3 times is 1080, like it just gets harder to count that. So oftentimes we measure our kind of angular values in terms of radians. We are not going to actually calculate anything in terms of sines and cosines with our radian values. So I don't want you to be confused or worried that, oh, sometimes I have to be in degree mode and sometimes I have to be in radian mode. We are going to leave our calculators in degree mode, and we just will not do any calculations with these radian values, okay? So with this concept of angular quantities, we're basically going to go and take a look again at all the different quantities we've looked at so far. So the first thing we studied were just motion, right? And so that was this idea of displacement. So angular displacement is just the angle an object sweeps as it moves, as it rotates. So our symbol for this is just the symbol for the angle, it's theta. Our units, they can be degrees or radians. We will often use radians. There's no outright equation for this, just like how there was no equation for displacement. It's just something you measure. It helps to keep in mind that one revolution is 2 pi rads. And the other thing to keep in mind is the link to the linear quantity. So if we think about the link to the linear quantity, that would be like how much of the circle the object is rotating. So if I think about something moving in a circle, and it starts here, and it rotates, okay? This is the angular displacement, but the linear displacement is physically like how many meters it travels, okay? And so this is also called the arc length, right? This is a little bit of review from geometry. So this is the arc length, and we symbolize that with an S. And the link from the linear quantity to the angular quantity is that, if I think about arc length, S is equal to theta times r, where r is the radius of curvature. Okay? So that's the angular displacement. The next quantity we looked at was velocity. So there's angular velocity. And this is just the rate at which the angular displacement changes. symbolize it with the Greek letter omega. And it's kind of like a W with like curves. All of the angular quantities have Greek letters for their symbols. So it's a symbol of omega. The equation for it is just kind of out of the definition. So it's the change in angular displacement over time. So omega is going to equal to a change in angular displacement, so a change in theta over a change in time. The units would be radians, so rads per second. And again, it's useful to have a link between the angular quantity and the linear quantity. So I'm going to call this link to linear. So the linear velocity of an object is equal to the angular velocity times the radius of curvature. Notice there is a similarity, right? We saw for arc length was, this is our linear quantity, it was equal to theta times r, okay? Oh, and that's going to be common. So that's angular velocity. Then just kind of going through the next one, that would be angular acceleration. So angular acceleration, this is going to be the rate at which the angular velocity of an object changes. Our symbol, again, it's the Greek letter for A, which is alpha. The equation for it is alpha is equal to a change in angular velocity over time. Units would be, so angular velocity is rads per second and divided by seconds. So this is rads per second squared. And again, it's useful to have the link to the linear quantity. And hopefully you kind of saw the trend. If arc length was equal to theta r, linear velocity was equal to omega r, chances are linear acceleration is equal to alpha times r. Okay? So this is looking at like what the linear acceleration, like meters per second to meters per second. What does that change from the meters per second here to the meters per second here? Okay. Now, here we have these angular equivalents of displacement, of velocity, and of acceleration. And if you have an object that is moving at constant acceleration, then you should be able to apply kinematics. So angular kinematics. Let's just remind ourselves of what the linear kinematics equations were. So linear kinematics, so this is movement, circular or rotational movement at constant acceleration. Rotation, I can't spell. I was a physics major. Rotational movement with constant angular acceleration. So let's remind ourselves of the linear kinematics equations. There was V is equal to V naught plus AT. There was delta X equals V naught T plus 1/2 AT squared. And then there was V final squared equals V naught squared plus 2A delta X. So same format of my equations, but now I'm going to use my angular quantities instead. So instead of V equals V naught plus AT, the first one will be omega equals omega naught plus alpha T. Okay? Second one is displacement is equal to V naught T plus 1/2 AT squared. So displacement, that's theta, so delta theta is equal to my initial velocity, so omega naught T plus 1/2 alpha T squared. And then that last equation, V squared equals V naught squared, so that would be omega squared equals omega naught squared plus 2. This is where it really gets confusing. 2 times acceleration, so that's alpha, times my change in displacement. So times my change, delta theta. And it's all Greek to me. So the equations, they just don't, they look daunting because it's in a different language, it's Greek. But in terms of your ability to solve, if you can keep in mind what the symbols are, and also what the units are, rads per second squared, if we're using some common sense in terms of knowing units, it should be pretty straightforward in terms of solving an angular kinematic problem. So we're going to go through one example of angular kinematics, and then we'll practice it more in person. So I should have that nearby. Here we go. Almost. A CD accelerates uniformly from rest. So it means its initial velocity is 0. So this marker is terrible. I want a better one. I think it's just been a while since anything was used in here. So they're like, let's see. Oh, that's good. So omega naught is 0, okay, because it starts from rest. So it accelerates from rest to an operational speed of 500 RPM. That's the omega value. But it's in RPM, and RPM is revolutions or rotations per minute, okay? So we're gonna have to convert that to rads per second, and we'll do that. That's kind of our first step. And this is our time value. First question says, what is the angular acceleration of the CV? So let's just start with that first part of the problem. Let's not worry about the second part. Let's convert this. Right now, I have that this omega value is 500 RPM. So that's revolutions per minute. I need to convert that to rads per second. So just a little bit of unit conversions. I know that 1 revolution is 2 pi rads. And that will get rid of my revolutions. And I know in terms of minutes, 1 minute is 60 seconds. So that will get rid of my minutes. And then it would get me into rads per second. So first step is just converting. Anytime you have an RPM value, converting that to a rads per second value. So take a moment, pause the video, calculate this out. This is just good practice. 500 times 2 pi divided by 60. You can either leave your answer in terms of pi or calculate it out numerically. I think I calculated it out numerically. So I got that it was 52.36 rads per second. Hopefully you did your own calculation. You're keeping me honest, making sure I didn't make a mirror. So that is my omega final. And the first question says, what is the angular acceleration of the CD? So I'm looking to figure out what alpha is. Okay. So thinking back to my equations here. I feel like Vanna White. Someday that's going to be obsolete, me saying that. Alpha is in every single one of these equations. So now we kind of have to think about what else do we know. We know that omega naught is 0. We know time. And we've just found omega. Okay, so we have omega, omega naught, time, looking for alpha. Hopefully you're seeing we're going to use this first equation, okay, because I don't have any understanding of what the theta value is. So if I use that first equation says that omega is equal to omega naught plus alpha t. So 500, not 500, 52. I can salvage this. 52.36 is equal to 0, that's my initial velocity, plus alpha, that's what I'm looking for, times 3.5. So alpha is equal to, again, pause the video, calculate this on your own. This is just good practice doing your own number crunching. I get that it is equal to 14.96 rads per second squared. Okay. Okay, the problem continues. If the CD comes to rest, so if it comes to rest, now I'm saying that this new part of my problem, my omega initial is 52.36. Like it got to that speed, and then now it's going to come to rest. And this happens in 4.5 seconds. So that's my new time value. It takes a little bit longer to slow down. what is the alpha? So you should be able to see that it's going to be the same equation, okay? We're just going to go to a stop. So this will be 0 is equal to 52.36 plus alpha times 4.5. Again, pause the video. My alphas are getting really wonky here. Calculate the alpha for the deceleration, so it should be a negative value. And I got that it was negative 11.64 rads per second squared. Okay, last part of the problem says, what is the how many revolutions occur during this time? Okay, so how many revolutions, how many times does it go around? So in order to figure out how many times it goes around, I need to figure out what the theta is. Okay, so kind of new part of the problem in this, I know that my initial velocity in this kind of deceleration portion, my initial velocity is 52.36 rads per second. I know that my final velocity is 0. I know it takes 4.5 seconds to do this. And I just found out that the acceleration that's causing this is negative 11.64 rads per second squared. And I want to find what theta is. Okay? So if I think about my equations, bring it back up here. There's two equations that have theta. This second equation has a theta value, and omega naught time acceleration time. I have all these. I could use this equation. But this third equation is also has a theta value, and it has omega, omega naught, alpha. I could use this one. Okay? You could use either one of these equations to find the theta value. It's kind of up to you. I'm going to use this one because I like omega squared. That's just 0 squared. So I'm going to use that third equation. Erase this. That third equation says omega squared equals omega naught squared plus 2 alpha delta theta. So 0 squared, I like that, 52.36 squared plus 2, my alpha was negative 11.64. So we can solve for the theta. So again, pause the video, crunch the numbers yourself, solve for what the theta is, keep me honest in terms of my rounding and whatnot. I got that my theta was 91.63 rads. Now, that's not the answer. In terms of I agree that this theta is 91.63 rads, but the question is asking how many revolutions occurred. So to figure out how many revolutions occurred, you have to do a proportion. One revolution is 2 pi rads. I want to know how many revolutions is 91.63 rads. Okay? So the number of revolutions is just going to be this 91.63 divided, I'm going to bring this over, right? So divided by 2 pi. Please be careful. When you actually do this in your calculator, you need to parenthesis that 2 pi. Otherwise, your calculator will think you want to take 91.63, divide it by 2, multiply by pi. Okay, so be careful, be careful, be careful. And calculate out the revolutions. So the number of revolutions that I calculated out was 14.58 revolutions. Okay. Revs, I guess, huh? So that is angular kinematics, very similar to what we did with linear kinematics at the very, very beginning of the class, but just looking at it in terms of rotational or angular quantities.